Swayam Prabha. Digital India. Educated India.
Welcome back to the organ printing course. In the last lecture, we have discussed about the vascularity, the need for vascularity, the anatomy of vascular structure, and then also what are the different strategies of vascular tissue printing. One such thing is the for generating lower microvascular channels or angiogenic modulation. In this lecture, we'll discuss direct printing of vascular constructs, actually how we can print a vascular channels directly in a either directly in terms of a to get a self-standing vascular construct, or also how to induce or how to print vascular channels within the tissue bed. So when we try to prepare the vascular construct, like suppose a self-standing vascular construct can be prepared by direct 3D printing of direct 3D printing by depositing different cell-laden hydrogels or media or cell-laden hydrogels using either extrusion-based or jet-based or lift-based bioprinting methods. So thereby, what's the study is done by Tarnatal. What they have done, they have vertically stacked the circles or pores within a J plan in concentric layers. But what they have done that, so it's a multi-nozzle extrusion-based system they have used, and with that, so they have what they have done, they have printed alginate-based cell and nitrogen hydrogel in a concentric cylinders, so that their design is like the outer cylinder or outer circular structure of 12 millimeter diameter, and the inner circular structure is almost 8 diameter. And then they have deposited the calcium chloride solutions in the inner circle, and then they stack that thing. They keep on repeating the thing again and again to create the 50 particle cylindrical structure. So this is their work. So what they have done, they have first optimized the layer thickness of tubular wire, then printing the multiple layers in vertical axis, and then depositing cross-linking it into the inner diameter wire, and then repeating this step again and again to reach to that 15 millimeter of height. So at first stage, they have used suppose one nozzle to print that alginate outer cylinder that is having diameter of 12 outer diameter and 8 inner diameter. So then stacking multiple layers of this alginate layer, they have got this concentric circular things to get some height, and then they injected or deposited that cross-linking agent. In this case, it is calcium chloride solutions within this printed area, and so that this calcium chloride solution will cross-link this structure, cross-link the outer cylinder, crossing the cylinder from the outward to from inward to outward direction, so that the structure get cross-linked and it is get stabilized. So by this thing, okay, actually by putting these concentric cylinders on top of each others, we can get something like a tubular structures. So this is the step by which they have printed the whole thing. And if you see here, this is the printed structure, where you can see clearly this is the inner diameter and the outer diameter, and then this is the channel width wall of the channel of the this is the channel direction, this is the channel, sorry, this is the channel width. You can clearly see this, and if you see here, this part is highly cross-linked because it is opaque. You can see clearly it is opaque in nature, and that the outer part, it is not, there is not the highly cross-link. Because of this, it is less cross-link because the cross-linker solution is present within this channel, within this pore here, and from there the cross-link solution is diffusing through the inner wall towards this side, right? So that's what happened when it is being like what is printed like this. and due to the cross-linking, the cross-linking happens in this way from this inward to outward direction, and because of that, inner opaque layer and the outer less opaque layer is present in this case. But the one disadvantage of this thing is spreading of the bottom layers. That always happens because due to the gravity, the when you put layers on top of each other, then due to the gravity or the weight falling on this thing, the base layer generally spreads, and you can get this kind of a slanting like structures we can get. So that is the disadvantage of putting this thing together. And this study they have done this study on limited that vertical printing shrinkage occurring. Other thing is the shrinkage occurring due to the cross-linking process. That is also another limitation of this thing. In another study, a HP diskjet 500 was used. Thus, that works on the principle of drop on demand inkjet printing technologies that we have discussed in our earlier lecture, where so they have used this Kui et al. They have used a biome composed of microvascular endothelial cells, and that is suspended in fibrin hydrogel, and then they have fabricated micrometer size channels with inkjet printing. So there are various reports based on these things, so where people have done directly, the people have tried to print vascular networks, and I'll urge you to go through literature. There are numerous descriptions available. I have just shown you here two things, this thing. So the two things. But one biggest challenge of direct printing of vascular construct is most of the time this vascular network, vascular channels or the vascular structure that is not self-supporting, and they just collapse, or as I've so this already seen when one study is spreading of the bottom layers happen due to the gravity. So one way to tackle that thing is 3D printing in the support bath. That concept earlier we have seen that. So one such attempt was done by Hinton et al., where they have used support bath material to improve the structure integrity of the biprinted vasculature. What they have done, they printed the same subvascular channel vascular tree in a support bath material, and their technology called Fresh, where it is freeform reversible embedding of suspended hydrogels. What they have done, they have used a syringe based extrusion system, where the extrusion based system, as earlier we have discussed, the syringe the extrusion based system, where we can load the hydrogels in that extrusion based system, and then we can apply pressure, like in this case that the pneumatic pressure was applied, and then, or not pneumatic, in this case the syringe driven pressure, or the that mechanical pressure was applied to extrude the bio. They have modified a MakerBot FDM bioprinter, FDM printer to load a syringe there, and to house a syringe there, and then they have loaded this their material in the syringe. In this case, also they have used a alginate material to load into the as a biowing, encapsulating the cells, and then no only the cell in this thing, and then printing the thing. So the support bath was used as a gelatin microgel support bath was used in this case, and the biowing solution printed within the gelatin support bath, and that provide the support, temporary support, because gelatin is a thermoreversible material. So during printing, the temperature can be kept below the transition temperature, that is below around 30 degrees centigrade, so less than 30 degrees centigrade. They have printed the structure within this hydrogel bath, and then on top of that they have used alginate alginate hydrogel for printing this kind of structures. So this is the printed dimensions, this is the printed dimension, that's what they have printed. You can clearly see this here, as the structure was like this, as this is going, the structure here, they have printed a vascular tree with the branching, accurately the printing the vascular branching within this hydrogel. So you see here the structure was in a gelatin microgel bath when during printing. Then what will happen, this If you remove the gelatin support bath, then we'll get this kind of muscular structure, right? So that structure you can clearly see here how the structure look like, whether the structure also the channels is quite visible here with this printing. That's the advantage of using the support bath material. But support bath material will hold the structure together and also help in formation of the clear channels and support structure. And also when they pass some media through this, it is very much the pores are open, or the inner luminal structure is open and you can pass through the thing. So this is a very significant advancement where support bath can very well use for printing a vascular tree with this kind of by printing method. The other method I'd like to discuss is this is a very interesting study where a similar support bath concept was used to develop a vascular channel embedded in a tissue bed. So here what they have used the organ building block. So these organ building blocks are developed by culturing IPSCs, even IPSCs, and then this the IPSCs they have cultured to form embryonic bodies, and those embryonic bodies are again further mature, and then they have used that is the thing they have used as a organ building block. And these embryonic bodies are again mixed up with the ECM solution. So the ECM solution here it is a matrigel. Matrigel is also a temperature sensitive material because at below temperature like around below 15 degrees centigrade or around that temperature it is in the liquid state. But if we can again bring the temperature to 37 degrees centigrade, then it will become solid. So they have printed this, they have suspended these embryonic bodies within the geometrical bath at low temperature where this so it is perfectly working as a support bath structure. And then they have allow it to settle this thing to settle down and to think so that they now this separate bodies will settle down, they will form a this kind of complex structure where then the supernatant was discarded, and then they have used a syringe. Actually the nozzle was inserted within this bath structure, and then they have a printed a gelatin printed a capillary like structure within this printed bath with the help of this thing. Now when we do that thing, then actually we can create right different kind of things. Here they have used a sacrificial ink material. Sacrificial ink is here is a gelatin was used as sacrificial ink material because gelatin has this gelatin also a thermoreversible material as we have discussed earlier. At below 30 below 30 degrees centigrade, it is becoming like a gel-like material. So they printed at as they printed at lower temperature. That temperature, the gelatin was very much intact as a gel, and then that was basically that you can create any kind of structures because this here your mixture that embryonic bodies in matrigel is acting as a support bath material, and your gelatin is using as a material as a bioink for making any kind of this kind of muscular network structures. So this is the one. So after this process is done, then what they have done, they increase the temperature to 37 degrees centigrade. Two things happen here. First is this matrigel, the that is ECM solution was used for this embryonic bodies. That solidified matrix solidified at 37 degrees centigrade because of self assembling of this thing. And also the gelatin liquefies at that temperature, and because of that the channels will be there but the gelatin will can be taken out, right? So that is the thing that happens first. That's what happened in this case. The first process is the adherent culture of IPS adherent culture. Then they are forced to aggregate using this kind of standard tissue culture, particular tissue culture plate, where this embryonic bodies will form or spheroids will form. These spheroids will grow further, and then the culture again this can be scale up, and then the cell aggregate suspended in ECM or gelatin sorry the matricial solution at below low temperature. This matrix compaction, and by centrifugation matrix is compacted and the supernatant was discarded. Then this thing was used as a support bath for printing the sacrificial ink. Gelatin was used as sacrificial mint ink here in writing into the granular tissue bath, and then the temperature was raised so that the sacrificial so that the whole this tissue bed with the material that will solidify, the gel become gel, and also the gelatin can be taken out. So this is the process by which the vascularized tissue construct can be fabricated effectively, and this process is called swift sacrificial writing into functional tissue. So this is the work they have done. So in this work they have also shown different types of embryonic bodies formation, like, and also actually 20 different types of spheroids or embryonic, this organ building blocks they have produced with this technique. And this is how actually this, like here we support at the first this tissue block, this a tissue, the embryonic tissue was developed within this kind of geometry, tissue culture plate, and then these embryonic bodies were collected, and then they were put together inside the material, and then again it is centrifuged. After centrifugation, you can clearly see a compact layer is formed here, and the supernatant is discarded in the compact layer. Within this compact layer, now you can actually immersed your syringe nozzle, and then you can start depositing the sacrificial ink. You can see nozzle here, and then the deposit in the nozzle, and the sacrificial ink, in this case that is gelatin, is getting deposited, and along the print direction a layer, a micro channel is getting formed within this tissue bed. That is the thing. And then the tissue bed, as you see here, microchannel, the tissue bed, a microchannel is getting formed, and these microchannels, after you can take out the gelatin by increasing the temperature. When the material will get solidified, also the channels, the gelatin will get liquefied at high temperature, and then gelatin can be easily taken out. You can end up in getting a channel like structures, print, evacuate, and perfuse, so that you can get a channel like structures, and by which you can perfuse your media and other things. So they have also shown different types of structures can be printed, or different types of channels can be embedded within this tissue bed. Actually, you can see here sacrificial link, a helical like structures have been also printed with the sacrificial link, and then that can be connected to the media, by, and media can be perfused through this thing. So this is the thing at printing. When the printing process is done, the helical like structure is getting printed, then the evacuate when the gelatin is taken out, and then you can again perfuse through the media can be sent within this. So this technology is a very very good for printing any kind of thing. Also in this same work they have also shown how a perfusal cardiac tissue can be fabricated within this thing. They have used the MRI data to find out the channels, or the vascular channels present within the support within this, in that part of this, a small part of this thing, a vascular tree present in the, suppose, in the heart muscle. So that's what they have taken out. This was isolated, and this was used as a CAD model for fabricating the structures. Now how they have similar way, as I have already discussed earlier in the earlier section, a the cardiac organoids were prepared from the same IPS. The cardiac organoids were prepared, and those were mixed with mixed with materials, and that was being put here. And then they have used a gelatin bioink, and then the inject nozzle was put, where nozzle in the, sorry, the syringe nozzle was immersed here, and then the channels were created within this cardiac organoid matrix here. And then actually then they say, actually this is the side view, front view, side view of the thing. And then that was allowed to set the hydrogel, the thing was allowed to set like here. The gel was allowed to cross-link at 37 degrees centigrade, and also gelatin was taken out, and then you can see perfusible channels have been created within this thing, right, within this thing. So this is how the cardiac tissue was fabricated by using this swift technique. This technique has got huge prospect for in terms of thing. So these are the few applications where direct printing of these vascular channels or vascular construct have been attempted. There are various studies where people have tried to generate vascular structure, either a self-standing vascular support structure or a vascular channels are created within this thing. So there are many such studies. Please go through the literature. Here I have also given the link for this few of the literatures. Please go through this literature. You will understand much better. And I'll discuss more of such things in the coming slides. Thank you.